welcome to the lecture number 3 for this course on peer-to-peer networks. So, in the previous lecture I had talked about voice over IP systems and how we use SIP server as a centralized entity, and we also then explored that how we actually partition the whole internet or whole actually world into domains, and each domain can have their own SIPs or SIP servers, session initiation protocol servers, and these SIP servers will also talk to each other. So, they kind of being acting as an entity on which everybody has faith, okay, and they are used basically to set up the connections between the two endpoints or two users who are communicating, and there is no mutual authentication required because that has been taken care of by SIP server. SIP server, everybody authenticates with SIP server, and SIP server actually know about each other through something called a SIP record, which is equivalent to MX record in DNS servers. So, but then I also further went on to mention that it is possible we do not require SIP servers, we can actually make a system where all the nodes together can start storing the indexes. They can start doing indexing of endpoints, endpoint addresses, basically phone number to the endpoint address mapping. So, here endpoint address is the IP address, the port number, the kind of transport which is acceptable to a endpoint, and once two endpoints know each other's address, they can actually can communicate with each other directly without having anybody as an intermediate. So, only thing which now has to be done is there is no indexing server, indexing has to be done in distributed fashion. So, I am going to talk about an algorithm which can actually be used. This is called distributed hash table. In the previous lecture I have talked about hashing, which was rendezvous hashing, which is truly where the everything gets uniformly distributed. Whenever a node dies off, all its responsible entries are being truly done, and we talked about consistent hashing. This is what we are going to use, and we also talked about inconsistent hashing. So, distributed hash table, or which is the CORD which I will be talking today, is an example of consistent hashing. We do not use rendezvous hashing because normally we assume that there will be large number of nodes which will be participating as an endpoint, as well as they will also be participating in the indexing, distributed indexing. So, on an average it will not be a very large number of entries which a node will be maintaining. Okay. So, on an average it will be only one entry per node which will be maintained. Okay. So, some of them may not be maintaining, in that case some others will be maintaining 2 or 3, but there are actually certain nodes which can act as called leaf nodes. So, leaf nodes do not participate in distributed indexing, but they are the having endpoint addresses. So, that possibility do exist. I will elaborate on these leaf nodes and the core nodes, or the nodes which participate in. So, I will be talking about CORD. So, CORD is a kind of distributed hash table which is very fundamental. So, this is an example which will be describing how multiple nodes, almost all nodes can participate and can talk about, can store the phone number to the endpoint address mapping distributively. So, let us move ahead and see how it happens. Now, what is the objective when we are going to build this DHT network? What we need to know, one of the very important criterion. So, CORD does satisfy that. In fact, all DHT network algorithms should satisfy this, that whatever happens, if a node is participating in the network, it should never happen that one node dies off and few other nodes are now separated from some of the other nodes. So, they cannot talk to each other because somebody who is an intermediate has died. So, that network partitioning should never ever happen. So, this has to be guaranteed. So, this actually can be done by something, a technique called logarithmic partitioning. So, that is what is used almost by all DHT algorithms. This also reduces the routing table size, So, this chord is an example of that. I will generalize on this later. Now, routing has to be such that you will search for a node which is closest to the hash of the key. Now, in our case we are looking into voice over IP system. So, telephone number is what is my key. So, I will compute the hash function of key. I have talked about hash in one of the previous lectures. So, hash is basically an computation. So, when you push in the key, it will just do some kind of randomization, will create a fixed number of bits. So, whatever be the size of input, output will always be a fixed number of bits, and this number of bits will be same as that for the node IDs. So, the node which is going to be closest to this hash, we should be able to reach to this particular node, and this closeness is what is going to be the metric for the root. We call it a root node. The node which is closest to the hash of the key is the root node for the key. So, that is the way we define it. It can be, if it is also possible in some network, in fact in CORD it happens that a distance from A to B, node A to node B, or node A to hash ID B, and from B to A, they are not same, they are different. It is asymmetric distance which exists. So, we have to, when we define a root node, we have to specifically tell whether I am looking for root of the hash ID. So, it is distance from hash ID to the node ID which has to be minimized, or node ID to the hash ID which has to be minimized, and depending on that my routing tables have to be framed. Okay. So, we should be able to build up a routing mechanism. So, node will only look at the hash ID which has to be routed to the root of it, and the routing table, or basically or neighborhood information, will find out the best match and send it forward to that guy, and this should keep on happening till the entry, till the message reaches to the root node. So, at root node, when the test will be done, it will find out that node itself is the only closest entry, no other entry in the routing table exists, and that should guarantee that it is indeed the closest node. No other node should be the closest one to the hash ID. This indeed should be the root node, that has to be guaranteed. Okay. So, this is basically the query forwarding mechanism. So, whenever a node finds itself to the closest one, the search will terminate, it will find out it is a root node. It will now look into its own database and find out if that key, that phone number is there in the database or not. If it is there, then it will check what is the corresponding endpoint address, and now it knows this is the endpoint address. So, whoever has sent a query, he will also send his node ID, so that again you can use same DST routing to send the reply back. It can again be done through a DST routing, or if the IP address and port number has been sent by the source node, a direct communication can also be done. So, source node will know what is the corresponding endpoint address for a phone number, it need not go to a server and find it. It is just finding out this phone number, who must be responsible guy holding this entry. Okay. Just find out, send the message to him, it has to be routed, and the guy will respond back. So, the actual user who is holding the phone number will also publish in the same way. So, when he is publishing, the entry is created by the root node. When somebody is querying, the entry is being retrieved from the database and sent back to the querying node. So, in fact, now this hash ID size or the node ID size, how much it should be. So, in fact, this can be any bit. In fact, the example which I will be covering is based on 4 bits, but in real life things mostly we choose a larger number of bits, generally 256, 512 or 1024, which actually means total 2 raised power 256 possibilities for the node IDs exist, and each node has to pick up from one of these values. So, but each node ID will now be of 256 bits, and so hash value. So, when I put a key into a hashing function, the hash ID which I get should also be 256 bit, and that is how the mapping, then whichever is the closest node as per the definition. So, which I will define as I go along for the CORD, what is the definition for the distance, whichever is closest, that will become the root node, and that guy must be holding the phone number to the endpoint address mapping. So, CORD is a circular organization, all nodes are placed in a circular fashion. Okay. So, how this will be done, let us see. Now, remember it is a logical organization, there is no need that if in the circular organization somebody who is next to me or who is previous to me, I need not maintain a live connection all the time with them. I just simply need to know what are their corresponding endpoint address for communication. So, whenever some message comes to me, I have to give it to my next guy in the circle, we call it successor, the guy who is previous to me I call it predecessor. So, the guy who has a lower ID than me is a predecessor, the guy who has a higher ID is a successor. So, I need to know only the endpoint address of the successor, I can then set up a connection TCP or UDP or maybe HTTP and transport the message to him. I need not maintain the connection all the time. So, it is a logical organization, not if there is no physical wire, it is a logically thing and connection need not be maintained all the time. It is done on need basis. Okay. So, this is an example I am showing, this is a circular organization you can see, and I have given a 16-bit number. So, 16-bit means each of the digit, there are 4 digits, each digit is represented by 4 bits, that is why I can use a symbol from 0 to F, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, then A, B, C, D, E, F. So, which is 15, 0 to 15, which is total 16 possibilities. Okay. And there are 4 such digits, so 4 into 4, 16-bit node IDs I have taken, and I have arranged in such a way you can see 3 to FD if you look at. So, in 3 to FD you will find out 1200 is the lower node ID. So, between 1200 and 3 to FD there is nobody else. So, you can actually look at all possibilities, there is nobody else indeed. And the guy who is the smallest node ID, but higher than 3 to FD is the next successor of 3 to FD, which in this case will be 5 to FF, and so on. This goes in a circular fashion. So, when it goes to FDE0, it just completes the circle. So, you have to again go from, it will go to FF. So, there is no FFF here, then go to 0000. So, FF is a predecessor of 000. If they exist, they are not existing here. So, 1200 is successor of FDE0. So, we are not using 256 bit here in node ID space, but we are using 16 bits, and immediately predecessor node, immediately previous node is the predecessor in this case if I am going in a clockwise fashion. Okay. So, when you are moving clockwise, immediately previous one is predecessor and immediately next one is successor. And very simple thing which we can do here, I will actually modify this definition. So, all node IDs if you look back here, so between 3 to FD, so any node, any hash ID which is higher than this, but lower than or equal to 5 to FF, all those hash IDs, if they are coming by hashing of the key, all those keys will be stored in by 5 to FF. Okay. So, this is what we are writing. A node is responsible for storing all key value pairs such that the hash of the key is greater than the predecessor, but it is less than or equal to the current node ID. So, then current node is responsible for holding up all these key value pairs. So, key in our case for voice over IP system will be phone number and value will be the corresponding endpoint address. Now, the question is if any new node comes in, how he will join the cord actually, how it will join this whole organization. It has to be placed at the right point. So, if you are for example joining here is by say 4200. So, 4200 can only be placed here between 3 to FD and 5 to FF. So, wherever whichever node it picks up, it has to ultimately should come here, there is no other option for him. So, that is the organization. So, how this will be happening? Okay. So, for example, in this case we have this circular organization. So, in this cord organization, so we have a node X which is already part of the cord. So, new node actually N will come, and let me have this node ID be ND. Okay. Now, this ND we have to figure out it is going to be in between which two nodes and it has to be placed there. But first thing, is that no other node should be actually using the same node ID, that is very important. If it is already using, then there will be a clash. Every node should have a unique node ID, that is one of the key characteristic of any DHT. So, in this case, this node, if when it generates a new node ID ND randomly, it will then first of all find out somebody, how this will be happening. So, normally few of the nodes are called as bootstrapping nodes. So, in any DHT network they are already well published ones. So, if you want to be a node, you will first of all just get that list, and that will become your neighbor, and when you want to attach, you will be always talking to them. So, a node N will talk to X and it will say, I have picked up this node ID ND, you please go ahead and find out if a duplicate exists or does not exist. Okay. So, then the node X will find this thing particular out. So, now this bootstrap node is a well advertised node, as I mentioned, and it can be used to join the network. So, that is a very fundamental thing, it always happens. Now, routing to a hash ID, R hash ID. So, this I will, whatever is hash ID, I will, the root node of this I need to find out. So, whatever this new ND is there, I will put this ND here and I will try to find out the corresponding root node. There is no hashing is required in this case. So, ND itself is acting like a hash ID. So, if there is somebody else who is actually having the same ND is being used, when I will use this root search, I will basically keep on passing till a node figures out I am the root node. So, if that node's node ID is equal to ND itself, then it is a duplicate. So, that is the case which I am mentioning. If the root of the node ID is the node ID itself, it is a duplicate entry, and if it is something else, it means it lies between this current node and the predecessor, and no node ID is using this particular value ND as of now, and that ND can be used by the new node. So, essentially the root of the value ND should be communicating back to node X and informing him that what is the value of the root of ND. If it turns out to be ND itself, it is a duplicate. So, in that case X will tell node N that you please can't use ND, please regenerate your node ID again. So, it can randomly pick up. In fact, I will give you a method by which this has to be done, because this has a flaw as of now, this is a security loophole. If you can arbitrarily choose any node ID for yourself, because in this case there is an attack called denial of service attack. So, you need not understand it now, I will explain it later on, but if you want you can search on the internet about it. So, that attack actually can happen, but because of the conceptual reasons I am currently assuming somehow this guy gets a node ID, but how it gets it I will explain it later in one of the later lectures. Now, basically in this case root of hash ID has to be found out. Okay. A node will check if the hash ID is between predecessor and less than or equal to the current node, search will terminate, current node is a root node. Okay. So, that is a logic, otherwise it is going to be passed to the successor node, you can simply keep on doing it. Now, the problem here is if the ND is supposed to be happening here, this is the root node. So, this will keep on moving all the way in the circle and will come back here. If you have thousands of nodes, so thousands of hops are required before the query can be resolved and replied back. We will solve this problem, but currently let us only keep it as a circle. So, it will take time actually. So, this is how it will be happening. Again I am explaining that new node X will search for root of X, new node has given this value, and it will ask the bootstrapping or any other node if it knows, and root of X is found to be X, node ID is duplicate, otherwise X can be used. Okay. Now, in this case the node which is starting the query, which is the bootstrapping node or who is participating in the DHT, has to actually in the query itself has to mention its own node ID, so that the reply can come back through DHT, or it has to give IP address and port number, endpoint address of itself, on which the root node can respond back directly, and then this guy will talk to the new node and tell him whether you can be inserted or not. Now, if it can be inserted, how it will be done? So, in this case, for example, I am showing a case here. So, this is again a small quad DHT, I have these node numbers 1, 5, 7, 9, 13, 14 and 15. node 10 is the one which gets inserted, and obviously when root of 10 is searched, it will turn out to be 13. So 13 will respond back and it will say there is a unique one, so you can use it. Okay. So node 13 is being informed by 1 that root of 10 is 13, so node 10 can be used. So 1 will now inform the new node and node 10 will inform 13 for insertion. Okay. So now the 13's endpoint address is available to node 10, node 10 can directly tell him that you kindly insert myself. So 13 has to tell about his predecessor to node 10 and it should tell node 9 about node 10. So 9 will now insert 10 as a successor, 10 will insert 9 as a predecessor, 13 as a successor, and 13 will add 10 as a predecessor. So 10 will get inserted into the chord ring. So that is how new nodes arrive. So every time nodes will keep on coming and this will happen. Nodes also can be removed actually. So normally one of the best way of handling this is, of course we can make a self healing system, that is how it is done in actual implementation. So now you can see node 10 is informed by 13 about predecessor as 9, node 9 is informed by 13 that new successor is 10, and 9, 10 and 13 make the entries and you have got the ring ready. Now nodes also need to keep the information about successor of successor, basically grand node, grandparent and grandchild. So you also need to keep who is a successor of successor and who is predecessor of predecessor. So first is the grandchild, second one is grandparent, and in case of a node fails, simply connect to your grandparent or grandchild. So depending on whether a parent or child actually has died, and this way you can immediately heal if a node failure happens. Okay. So if you find your parent is dead anyway, so you have to now just connect to your grandparent because that information is also there. Even if it is not there, you can still heal. The problem is to be done in a slightly different way now. Okay. So in fact the best algorithm which is used as of now is that all nodes will maintain these kind of neighbor tables, they are also called routing tables in DHT, and periodically to all the neighbors which are listed, this neighbor table is being communicated. If my neighbor table changes, then also I will communicate to all my neighbors. So as the neighbor tables are being received from my neighbors, I may get new information about new nodes which then can be used to basically improve my current neighborhood table or routing table. Okay. So this process will keep on happening, and as I get better and better option for the nodes which can be put in routing table, I will keep on updating them, and at some point the routing table will stabilize. So that is what essentially will be the chord. Even if a disturbance happen, it will be for some time, and after which again it will stabilize back to another stable ring topology. And I think one of the things which we do is triggered update in all these. This is whenever my own routing table changes, I should immediately send the copies to all my neighbors. If there is no change, I will do it after the period after which it should be done. So maybe every half an hour you are supposed to send an update, you will keep on doing it every half an hour. But if there is a local change happens, table change happens, then I have to do it immediately. So as a consequence, wherever the table changes are going to have an impact, only those nodes the table will be updated very fast if there is a change which is supposed to happen. It will not go into area where table change is not going to happen because of the actual change, whatever is happening. So that triggered update kind of stabilizes the routing tables very fast. Now what will happen when the nodes, this is node actually dies off. For example, node 13 has died off here, and I am assuming that we are not maintaining grandparents and grandchildren. In that case also it is going to work. So 10 for example will get from 9 the information about 7, that is his neighbor, is a 9 is telling the neighbor table update has been sent to 10. So 10 will know, okay, I am not getting only entries coming from 9, okay, for 14 it does not have an entry, 13's entry will expire because 13 is dead, it is not sending the update, periodic update, it will make an entry for 7. Similarly, 14 will make an entry for 1. So, they kind of 2 sub rings will get created, and of course, the rule is whenever somebody is informing me, I know whatever nodes which I know, which even not are there in my neighbor table, I should still send my routing table update to them. So, as a consequence, 7 will send its update next time about 5 and 9 to 10 also, as well as to 9 as well as to 5. So, 10 will come to know of a new node 5, 14 will also come to of new node 5, and they will update, and that is a new updation which will happen. In next step, essentially 5 will send about the information about 7 1, which are actually routing table, to 10 and 14 also. 10 and 14 are not in routing table, so their information is not being distributed by 5. So, 10 will now update to 1, 14 will to 7, and so on, and ultimately ring will get formed, 10 will get connected to 14, and topology repair will happen. And since it is done because of the triggered update, this will keep on happening pretty fast. Now, if I create only a ring, there is a problem. If there are large number of nodes, average number of hops for a query to reach a root node will roughly be n by 2, half of the circle, okay, on an average. Otherwise, you have to do either a full circle with some probability, sometimes only with 1 hop, on an average n by 2. If n is very large, this is going to be a slow process. So, query discovery should be actually fast process, not a slow process. So, we can improvise on this. So, the improvisation is using finger tables. We call them finger tables because they look like shortcuts being done, it is not a circle. In general, we can call them routing table or neighbor tables actually. So, each node will keep information about more number of nodes, but which nodes, that is a question which remains. So, should each node keep about information about everybody? So, if there are 1000 node, I have to make 1000 entries, every node has to maintain, that also is not logical. Okay. It is like a full connected mesh, which can happen with low number of nodes, but not for large number of them. So, maybe what we can do is I can create a successor, I can maintain a predecessor, I can also take a node which is the root of the halfway across entry. So, if my current node ID is whatever it is, I go halfway across, find out what is the corresponding root node, that is my middle entry actually. So, I will find out if a query has to go between S and this. So, it is closest to this one or closest to this one, I can hand over correspondingly. Similarly, I can do handover to P or this, depending on it is closer to which of the entries. Okay. So, that could be one way. I can further actually expand on this. So, this is an example which is given, that I have given node numbers 2, 5, 7, 9, 10, 12 and 15 in this code, and I am looking for a 9th entry. So, 9 will have a successor as 10, predecessor as 7, but what would be middle entry? So, there are total 16 possibilities here, it is a 4-bit node ID space, for simplicity I have taken that. So, 16 by 2 is 8, so 9 plus 8 is 17, 17 modulo 16, which is going to be 1, and root node for 1 is 2, so 2 will be the middle entry. Okay. So, when I want to, I can actually also now have a distance from I to j, node I to node j can be dj minus di plus 2 raised power n modulo 2n. So, basically if a node is here between 12 and 15, so that node to 15 whatever is the gap, that is going to be my entry. If a entry is between entry is 14 and between 14 and 2 I want to find out the space. So, when I go from 14 to 2 in cyclic fashion in clockwise direction, that will be distance. So, this function gives exactly that value. Okay. So, in fact, if from 15 to 2 what is the distance? It should be actually, if after 15 you will get a 0, 1 and 2, it should be 3. So, I can actually say 2 minus 15 I cannot have, it will become negative value. So, I should add 16. So, 2 minus 15 is 13, 13 minus 16 is going to be 3, and 3 modulo 2 raised power n is 3. So, 3 will be the distance from 15 to 2, not from 2 to 15. So, 2 to 15 distance if you want, that will be 13, 15 minus 2. So, I to j is a directed graph kind of thing. So, I to j distance is not equal to j to I distance. Okay. So, that one should note. So, we can actually say 3 to j, the node j will be the root node if I am searching for a root of node hash ID 3. So, 3 to j distance should be least, so then j will be the root node. So, that is for example, what I would like to search. So, in that case I will find out 3 is going to be in between which value, between 7 and 2. So, I will just send it over the query to 2 and 2 will find out who is the next guy, who is the successor 5, it will hand it over to 5. 5 will know that is between my predecessor which is 2 and myself which is 5. So, 5 should be the root node, that is how it is going to happen. Okay. In fact, when middle entries are not maintained, this extra entry which is part of the finger table for making the things fast, you can actually do it both ways. You can do it clockwise search as well anti-clockwise. Ideally, if I implement algorithm, so I need not always go clockwise because I have predecessor successor both. So, for example, I want to search for 3. So, I will just simply say whether 3 lies on the left half of the right half. So, diametrically opposite number for 9 is going to be 1. So, 3 is more than 1. So, it lies between on the left side. So, it is good to actually send it via predecessor, probably that will require lesser number of hops assuming uniform distribution of nodes. Otherwise, if it is between 9 and 1, then in that case give it to a successor. So, this actually entry for search will going from 7 to 5 and 5 will then figure out that it is a root node and it will stop there. Okay. And if root of 13 you have to find out, it will go through a successor route. If I am not using finger tables, that is the way it will be happening. So, I can do bidirectional also. If finger table is there, you will simply give it to between, you can hand it over to 2 and 2 will then further give it to 5 and 5 will say that I am the root node. So, I can now expand on this finger tables, I can need not keep only one entry, I can keep many of them. Okay. So, normally it will be like root node definition can be modified. So, I am modifying it slightly, I am not going from distance from hash ID to node ID, now I am looking at a distance from node ID to hash ID. See, I have used hash ID first, hash ID minus node ID actually here. So, as a distance from the node ID to hash ID which is going to be minimum, that node will be the root node. So, I have now inverted the definition. So, this need to be minimized, find out the node for that. There is a reason for doing it because it makes routing much simpler and even testing to figure out whether I am the root node or not also simpler. So, now x is the current node at which I am, and now I want to find out the finger table entries. So, I will now search for the halfway across entry. So, x and there is a diametrically opposite entry. So, this will be x plus 2 raised power n minus 1. So, if it is 2 raised power n is 16, it will be 8 in that case, modulo 2 raised power n, find out the root of that, okay, the node which is closest to that, but which is smaller. So, that is what essentially this distance actually means. So, that will be the first entry. Then I can do a quarter 2 raised power n minus 2 and so on till I get x plus 2 raised power 0 mod 2 n. So, in fact, I can actually keep n entries in my routing table where n is number of bits. So, in this case it will be 4 routing table entries, but if n is 256, should I make 256 entries? I need not, I can actually make say lower side entries I can make where it goes from this 2 raised power I. So, I goes from 0, 1, 2, 3 and then on the higher side I can go from 255, 254 or something, and middle values I need not keep. So, I can actually keep a shorter table. So, I can do a jump around and still converge much faster than using only a pure circle. So, in this case for example, look at node 9. So, I am taking the same DHT. So, it consists of 2, 5, 7, 9, 10, 12 and 15 and I am looking at a node 9. So, I take value of I. So, if it is 0, so this is the first finger table entry, 9 plus 2 raised power I, 2 raised power 0 is 1, 9 plus 1 is 10, modulo 16 it remains 10 and for 10 the root node will be whatever is this value, this minus node ID plus 2 raised power 4 total sum and then modulo of 2 raised power 4, that is what I should be using. So, for this the root node will be 10 only, okay. Then 2 raised power 1. So, 9 plus 2 is 11, 11 modulo 16 is 11. For 11 the root node is 10 because 10 is the closest one, lower and closest as per the definition which I have given here, the same definition. with I is equal to 2, it becomes 9 plus 4 13, and 13 is more than 12. So, 12 should be the root node here, which I have put in here, and then 9 plus 8 is 17, modulo 16 will be 1, okay. And if I look at the distance, so 15 will be the closest one, okay, because it is actually lying between 15 and 2. So, this is the root node for 3. Now, for handing over 3, I will find out the distance from any one of these entries. I am looking at a node hash ID of 3, who is the root node of that. I will just compare with each one of these entries, whichever is closest I will hand it over to it. So, distance from node to 3, remember this is as per the definition which has been given here, which I have made a change from the first case. So, this will become 3 minus 15 plus 16, modulo 16, this will become 4. Okay. So, this is 3 minus 15 will be 12 plus minus 12, minus 12 plus 16 is 4, 4 modulo 16 is 4. So, 4, this 15 will give the least distance. So, I will hand it over the packet to the 15, okay. And you can actually see for node 3 it is a 2 which is going to be the root node, not 15. So, 15 has to do the same exercise again. So, node 15 will now also maintain its own routing table. So, for 0 it will be 15 plus 1, which is 16, modulo 16 is 0. For 0 I think if you go back and see the figure, 0 for 0 and 1 the node root will be 15. So, I will put 15. Again when I is 1, 15 plus 2 is 17, which is going to give after modulo operation as 1. Node ID 15 will be the root node. When I is equal to 2, it is 15 plus 4, 19, modulo 16 it will be 3, root node will be 2, and for 3 it will be 7. When we are going to compare the node hash ID 3, we will figure out 2 will be the closest one. So, we will hand it over to 2. Second hop, 2 will now again do the same exercise, it will have its own routing table. So, 2 plus 1 is 3, so routing the root node for that is going to be 2, 2 plus 2 is 4, root node is 2, 2 plus 4 is 6, root node is 5, 2 plus 8 is 10, root node is going to be 10. Okay. So, these will be root nodes, and node 2 will figure out this still remains the closest node to hash ID 3. So, node 2 will declare that I am the root node, and it will now search for the corresponding query in the database. So, in fact, if we are going to use 256 bit node IDs, this is a pretty large number. We can actually have at best 256 entries in finger table at each node. In fact, I am telling the middle entries need not be used. In fact, for some of the entries you will get the same root node. So, you can actually see that I am getting for 2 entries 15, I am getting here again 2 entries 10. So, I can combine 0 to 1, it is 10 only in one single entry, I need not maintain multiple of them. So, I can compress the finger table, and of course, this is a property which will always be maintained. So, here for example, root of y has to be figured out. Root of y is this particular red node. So, it is I am starting from x, x will now we have a property, we have actually dx a b c. So, dxc from x to c the distance is always going to be greater than dac from a to c, this property is always going to be maintained. This distance can never be larger than x to c distance. Okay. So, same is going to be true for dbc and dac if I compare, and if I compare dcy similarly, and between dby. So, every time you are going to the closest node. So, x will have only these 3 entries. So, day, dby will be larger, but dcy will be the least. So, I will hand it over to dcy, and every step you always tend to go to the closer and closer to the hash ID's root, hash ID essentially, and when you get the closest node that will become the root node. So, we can change the root node again, but my routing table will change. So, somebody says okay, I am going to now the root node will be the guy who is next from the hash ID. So, the distance which is we are going to minimize is node ID minus hash ID plus 2 raised power n and modulo of 2 raised power n. Now, this is different than the definition which I have used earlier. Here node ID and hash ID has been swept in the later case. So, I will not be using plus here, I was actually making finger tables on the successor side. You can see here I am always making on this. So, halfway across on this side, quarter on this side, 1/8 on this side, and so on. Now, I will start making routing table on this side, okay, in the opposite direction, because I have changed my distance metric. Now, this is how it will look like. So, for 0 I will be doing x minus 2 raised to power 0 plus 2n modulo 2n, and so on. Every time it is a minus sign this time. Again these are n entries which need to be maintained, and search will terminate when a node finds it is the closest from the hash ID. Now, from the hash ID, it is not 2, in earlier case it was to the hash ID. Okay. So, take a case here when hash ID is 12, search will start from node 7, finger table for node 7 will be 7 minus 1, okay, and as per the definition it is going to be node ID minus hash ID, that is what we are using, okay, you can see here. So, based on this the root node will be 7. For I is equal to 1, 7 minus 2, it root node will be 5, 7 minus 4 again 5, and the last entry in the finger table it will be showing 15. So, when I am searching for 12, I will find out 15 will be the closest node. So, 7 will hand over the query to 15, 15 will again now build a finger table. So, for I is equal to 0 it is going to be 15, same logic 13, 11, then 7, and 13 you will find is closest from node 12. Okay. So, it is from again hash ID to node ID, that is why I have written 12 is the hash ID. So, we will hand over the message to 13, again 13 will build up the finger table, and 13 will be the closest from node 12. So, search will terminate at 13 and 13 will be the root node. Okay. So, 13 is, so 12 lies somewhere here, so the next guy. So, this is the way it is working. So, it is very systematic, you always use one single distance metric, and based on that you build your finger table as well as your routing strategy and as well as for the root node criterion. All three are actually using similar metric. Now, also one thing which you will do is that notice that what the way I am doing partitioning, let me go back to the figure, I am going halfway across 1/8, 1/4, 1/8, 1/16. So, 1 by 2 raised to power I, that is what I am using. So, I am actually logarithmically increasing, reducing the size of partition, and I am trying to find out the node in that. It is not of course the closest node here, but in general when you build a DHT it has to be closest node in a partition. So, let us see what is this logarithmic partitioning is actually conceptually. So, this is what we call logarithmic partitioning. So, look at this node n. So, you are want to build up a routing table for this. So, whole node ID space will be partitioned to two halves, A n, the remaining of A. So, the node which is in A closest to this node n will be maintained by n, only one entry from this half. Okay. Then whatever is the remaining part, this will be further divided into two halves, one is B, node n is not in part B actually. So, the closest node from B is also going to be maintained by n. Then wherever is this part, this will further divide it, this will be now 1 by 8. So, C, the closest node from C will also be maintained by 8. Then whatever is the remaining part, I will further divide it into two parts, one comes 1 by 16th part which is D. So, closest node from this will also be again maintained by this node n. Further division 1 by 32. So, again closest node will be maintained, and within its own partition all the nodes will be maintained by node n, which is the partition F. Okay. So, all nodes in the smallest partition, for example F in this case, will keep track of each other, and all these nodes also keep track of the closest nodes in exponentially larger and larger partitions. We are also doing almost something similar in the chord. So, closest node in E, this is the what how the routing table will look like. So, all nodes in the smallest partition, closest node in E, D, C, B, A partitions. Now, even if a single node is alive in the smallest partition, it will remain connected, because it is connected to everybody else, and each one of them is connected to one node in every other partition. Okay. So, this maintains a guarantee, and what is true for a node which is smallest partition is true for every other node, because everybody is behaving in the same way. So, that actually is a proof that logarithmic partitioning always maintains the connectedness property inside the DHT. In fact, that is the reason why it is used there. Routing table maintenance, as I mentioned earlier, that all nodes should periodically exchange their routing tables. So, in fact, you should, whatever nodes you are aware of, you will send your information to all of them, even if they are not existing in your routing table. So, every node is getting lot of updates from other nodes about the new nodes. So, some of them may not be there in the routing table. So, you will now search for these nodes. For example, in partition A, if you are somebody's closest, next time that guy sends all its neighbor table to you, you find some other node is also in that same partition, but it is more closer than compared to what was the earlier value, you will replace it. So, this will be happening all the time for all partitions, and you will be maintaining ultimately optimal and a stable routing table configuration. Okay. So, this is the way that you maintain a DHT thing. We will actually further look into the next lecture how study more about these DHT routing tables, and we will generalize this concept in a more elaborate fashion.